Welcome to a slow, beginner-friendly lesson on password hashing, made for absolute beginners. Stakes are high. Today we cross into the most security-sensitive topic in the course, passwords. If you remember one rule from this lesson, remember this: never store a user's password as plain text. Not in a file. Not in a database. Not in a log. We always store a hash of the password, and not just any hash, but a deliberately slow hash with a random value called a salt mixed in. We meet salts, we meet slow hashes like bcrypt and Argon2, and we learn the safe built-in Python offers for this job. The cardinal rule of authentication: never store a password as plain text. Not in your users table. Not in a config file. Not in a log message. Why? Because databases leak. Logs leak. Backups leak. If any of those contains plain text passwords, every user's account is exposed immediately, and because people reuse passwords, every other service they use is exposed too. The fix is simple: hash every password before you store it. Plain text is catastrophic. Here is what not to do. A dictionary mapping usernames to plain text passwords. Password 123. QWERTY. If an attacker reads this dictionary, from a backup, a leaked log, a SQL injection, they have every password immediately. And because users reuse passwords, the attacker can try those same passwords on email, banking, and social media. This pattern is the single most damaging mistake in application security. Never do this. What not to do? Here is the first key idea: the salt. A salt is a random value you generate freshly for each user. You combine the password with the salt and hash the combination. Because the salt is random and different per user, two users who choose the same password end up with completely different hashes. The attacker cannot precompute a table of common passwords because each salt changes the answer. Same password plus different salt equals different fingerprint. That is the whole trick. Same password, different hash. Watch the salt work. Define hash PW that takes a password and a salt, concatenates salt plus encoded password, and hashes the combination. Generate a fresh random salt for Alice with secrets.token bytes. Generate another fresh salt for Bob. Hash password 123 for both. Even though the password is identical, the hashes are completely different because the salts differ. An attacker who steals your database cannot even tell that Alice and Bob chose the same password. Watch the salt. Why does salt matter so much? First, it defeats rainbow tables, the giant precomputed lists of common password hashes that attackers download. With a peruser salt, those tables become useless. Second, it hides the fact that two users chose the same password. Third, it forces the attacker to crack each user's password separately. They cannot crack the whole database in one sweep. Note that the salt is not a secret. We store it next to the hash. Its only job is to be random and unique per user. 3 protections. Plain text passwords are the worst mistake in security. One breach and every account burns. Never plain text. Here is the second key idea. SHA-256 is fast. That is great for hashing files but terrible for hashing passwords, because fast means an attacker can try billions of guesses per second. Password hashing is deliberately slow. The goal is to make each guess expensive. If one guess takes 1/10 of a second, an attacker trying a billion passwords is suddenly looking at decades, not seconds. Slow is the feature, not the bug. Slow is what protects your users when the database leaks. Slow is the feature. 3 algorithms dominate modern password hashing. Bcrypt is the battle-tested veteran, widely supported across every language. Argon2 is the modern winner of the password hashing competition, the strongest choice when you have the library available. PBKDF2_HMAC is the safe built-in shipped with Python's hashlib, no extra install needed. Any of these is fine. What is not fine is plain SHA-256 or MD5 for passwords. They are too fast. 3 good choices. Add a pinch of random salt and the same password becomes 1,000 different fingerprints. A pinch of salt. Never roll your own crypto. This is a hard rule, repeated in every security book, because the failure mode is invisible. A homegrown hash scheme looks fine. It runs. It produces output. And then one day a researcher finds a flaw and every password you ever stored becomes crackable. Cryptography is a specialty discipline. Vetted libraries like bcrypt, Argon2, and PBKDF2 have been attacked by experts for years. Use them. Trust them. Do not invent. Use vetted libraries. Here is Python's built-in password hasher. Generate a random salt with secrets.token bytes. Call hashlib.pbkdf2_HMAC with the underlying hash name SHA-256, the encoded password, the salt, and a number of iterations. 100,000 is a reasonable minimum. Iterations is the slowness dial. Each iteration runs the underlying hash again. The function returns the salt and the derived hash. Store both. We will verify against them later. The built-in way, the iterations argument is the slowness dial. 100,000 is on the fast side. 200,000 is a common default. 600,000 is a modern recommendation. The rule of thumb, pick the largest value that still lets a login complete in about half a second on your production hardware. OWASP, the Open Web Application Security Project, publishes current recommendations and updates them as hardware gets faster. Check yearly, and raise iterations over time. Tune the slowness. Verifying is just rerunning the same computation. The user types a password. You take the stored salt for their account, the stored iterations count, and run pbkdf2_hmac again. If the result matches the stored hash, the password is correct. Plain double equals is fine here because both sides are random looking bytes and there is no timing leak that meaningfully helps an attacker who already has the salt and hash. The salt and iterations live in the database, the password never does. Rerun and compare. For passwords, slow is good. Slow means an attacker cannot try a billion guesses a second. Slow on purpose. Here is the full life cycle of a password. A user registers, they choose a password. You generate a fresh random salt. You hash the password combined with the salt, using a slow algorithm with many iterations. You store the username, the salt, the iteration count, and the hash. The password itself is thrown away. Months later the user logs in. You look up their salt and iterations. You hash the input they just typed using the same parameters. If the result matches the stored hash, the login succeeds. The password is verified without ever being stored. The life cycle. If you have a third-party library budget, Bcrypt is the most widely used option. Install Bcrypt. Call hashpo with the password bytes and a fresh gensalt. The library generates a salt, embeds it in the result, and returns a single string that contains everything needed to verify later. To verify, call checkpo with the password bytes and the stored hash. It returns true or false. Notice how clean this is, no manual salt handling, no manual iteration count. The library does it all. Most popular library, Argon 2 is the modern winner. Install Argon 2-Xfi. Create a password hasher. Call hash with the password and you get a single string encoding the algorithm, the parameters, the salt, and the hash. To verify, call verify with the stored string and the input. It raises an exception if the password is wrong. Argon 2 it is the recommended variant today, it resists both GPU and trade-off attacks. If you can install a library, Argon 2 it is the strongest choice. The modern choice. Cryptography is a discipline. Use the well-tested libraries. Never invent your own scheme. Never roll your own. Rules of thumb. Always use a vetted library, Bcrypt, Argon 2, or pbkdf2_hmac. Always generate a fresh random salt per password. Never store or log the plain text password anywhere, not in the database, not in a log, not in a config file. Never use MD5 or plain SHA-256 for passwords, they are far too fast. Never roll your own crypto. If you remember these 5 rules, your users are safer than most of the internet. 5 rules. What goes in the database row? The username. The salt, random bytes of at least 16. The iteration count or other algorithm parameters, so you can raise them over time. The hash, the derived bytes or the encoded hash string. What does not go in the database? The password itself. Ever. Anywhere. A database leak should reveal salt and hash and nothing that lets an attacker log in directly. Store these 4 in one breath. Never store plain text passwords. Salt makes the same password hash differently per user. Slow hashes like Bcrypt, Argon 2, and pbkdf2 hurt attackers by making each guess expensive. Never roll your own crypto. Use vetted libraries that have been attacked by experts for years. Your users trust you with their passwords. Hash them properly. In one breath. Next we step back and meet encryption. Where hashing is one way, you cannot recover the input, encryption is two-way, you encrypt with a key and you decrypt with a key to get the original back. We meet symmetric encryption with one shared key, asymmetric with a public-private pair, encryption at rest versus in transit, and the cloud service that manages keys for you. Hashing and encryption together cover almost all of everyday security. Encryption next. If you want practice, hash a password with pbkdf2_hmac using a freshly generated salt. Save the salt and the hash in variables. Then simulate a login attempt with a wrong password, rerun the same computation and compare. You will see no match. Now run it again with the correct password. Match. That is the entire authentication loop in miniature. Plain SHA-256 with Assault would look the same, but it would be far too fast. Try it end to end. When you store passwords the right way, even a full database leak reveals almost nothing. Stored the right way. Thanks for learning how to protect passwords. Next we meet encryption. See you on encryption.